So then studying about this claim tunneling, what we can observe in this graphene-like structure. So in quantum mechanics, what I can say about this claim tunneling is like in quantum mechanics, an electron can tunnel. Professor C.C. Roy is in ISI Kolkata is working on this tunneling time for quite some time. So few of his work is like Schrodinger-Langevin equation and ion transport for nanoscale. Then distributive effect and tunneling time also validated. Then weak value of dwell time, and the latest is that published in review letters. So that is on Hartmann effect and tunneling time. So, so here under him my thesis will be like will consist of many of the parts. So I will tell about all those parts and things what I am planning to do. So technically it is first it will involve the study of quantum tunneling for its transformability and reflectivity for different geometrical structure, which is already available in many works. I will do my write-up and put my things in this present or previous work, whatever it is done. Then the graphene structure and tight binding model. So as you know, this band structure in graphene is depending on this tight binding model. So there will be one study on this tight binding model, and the other fermions, then quantum Hall effect, which can be responsible for developing this quantum computer also in some time. So, and besides this is edge state in strong magnetic field and lattice distortion and all these things would be I'll put in this study. And then this quantum transport in this graphene, what will be my main work, the calculations for multiple barriers in the time one electron take for crossing multiple barriers in a graphene. So basically in quantum mechanics, an electron can travel through a conduction to valence band, and thereby avoiding this backscattering, and also for a non-zero in quantum mechanics, what you can say that an electron can travel through this conduction band to valence band. What we can call it, we can call it a interband tunneling or claim tunneling. It is already available, work is there. So I know this carbon atoms, whichever it's available in 2D, this one layer of graphite is called this graphene. So in this carbon atoms in a 2D honeycomb lattice near the K point Brillouin zone, the electron energy spectrum exhibits a linear dispersion that can be well described by the massless Dirac equation. So my study will be on this massless Dirac equation, whatever has been done and whatever I am doing. The unique chiral symmetry of Dirac particle results in transmission probability passing through high and wide electrostatic barriers. However, in the practical application, suppressing the claim tunneling effect is the key issue to effectively control and manipulate the graphene based device. So this claim tunneling may be responsible for developing this graphene based electronic devices. But I can say, so some papers are focusing on tunneling time in graphene based magnetic barrier nanostructure, Hartmann effect. Although from the latest publication we know that there is no Hartmann effect, but it was studied for some time. So I will try to compile all the studies in the thesis, and the dependency of incident angle and energy of the carrier and influence of spin orbit effect are the invariant for this tunneling of 2D massless Dirac particles. There had been a claim that for the particles in the case of claim tunneling, that is the complete transmission through a barrier, the tunneling time just equals the barrier width divided by the Fermi velocity. So we have to like in this work under Professor Cicero, I will be trying to validate all these things. And does it valid for multiple barriers also, or what will be happening after crossing the first barrier in the massless in the graphene barrier, in the multiple barrier in graphene. So in the end I will be completing. So in the end I will be completing the thesis work with all the current applications of graphene and its applications mostly in electronic devices which can be in future. So in Ghent University, in the group of Professor Stephen Courtnier, my work can be related to anything, which my main thesis, which is I am doing it in Indira Gandhi Center for Atomic Research. It involves like mechanical engineering, a bit of material science, a bit of a chemistry or metallurgy. So I can do work on all these things, and under Professor Stephen Courtinier, I have seen there are many works like this. Whatever I approached before for working in this, working the how grain boundaries affect the strength of a tungsten alloy in fusion reactors. So that kind of work I can do, and other work like whatever it has been done under his guidance is like atomic scale modeling of grain boundaries, role of impurity in copper. So it will be like very much related to whatever I am doing it here, if this kind of works are available, or like hydrogen trapping in steel, and this kind of thing is like it's right now I'm doing on this thing only. My work is titanium modified steel, and steel is like everywhere in this Indira Gandhi Center for Atomic Research. It is the main thing they are working on. So if I need to prepare for working in steel specifically in the second part of my thesis, so I can do that. And next is like ab initio prediction of material properties for inner core of planet Mercury. So if this kind of work is also available, this will be the most interesting work I have still done. So I have never done this kind of work, so I'm really interested in working in this applied physics or applied chemistry or molecular dynamics, this kind of part. Or like if I say it from the perspective of graphene, then we can also study it if not the quantum properties of graphene, then other works like the mechanical failures of graphene. That's also a point of discussions now. There are a lot of modeling, designing, computational work on in torsional effect or in tension or in compression, how these graphenes are reacted. So I went through a few papers on this kind of topics, and other works is like crystal structure prediction of supersaturated A2O, like in case of Zn3 Al2O6. So in this kind of work also I can get involved. So I currently I am giving my best effort to learn and to work a lot on this material science perspective in making materials. So I talked to another professor quite some time back. So it's like your master's project should be very much related to whatever you have learned in your first year of course studies. So in my course studies, if I say it involved many things, like it had nanotechnology to physical metallurgy, it has all these things, and basic mathematics and finite element method, and all these things were there. So the kind of work what I think about material science is like it's a combination of physics, chemistry, metallurgy, mechanical, and all these things. So I'm open to work in all this part of this engineering and science, so it's not a problem about that. But if I get to work in graphene, it will be good, because after reading about this graphene and papers and all these things, it interests me. That's the point. But it's not like that I can't work in anything else. Like what I'm doing here is like this titanium modified steel, and checking its workability for torsional purpose, which hasn't been done before. So I hope to publish a few papers before I finish up this part of my project. Not published, I hope I will be submitting this. So in the next semester, from January to May, there will be exactly 5 months where I can utilize those time I want to, and I'm interested in spending the time in Ghent University. And from my point, actually for my PhD, I want to continue in Europe. Somewhere I don't know, wherever I will be getting suitable positions and a suitable project, I want to get involved there. So this is the thing I can say. And this interest of physics is like it's always there for me. And in India, it always doesn't depend on your interest. Sometimes you study because you have to study few things. So it happened like that. I studied mechanical engineering, but most of my interest, it involves this study of applied physics, whatever I've mentioned till now. So that's why when I got a simple torsional experiment on titanium modified austenitic stainless steel, I showed the interest to work on molecular dynamics to my guide here, Mr. Utpal Bora. And he is very open to all these things. He doesn't have any problem if I work on other things, keeping my main project, doing my main project. So that's all the thing I can say. So we can talk in mail. So thank you.